now for our last lecture. I think that especially after yesterday, everybody knows Professor Willem Novák. Willem is a brave man because almost a week ago, we have obtained this bad news from Laura de Miguel, who was originally planned to have a speech now, that she cannot come and so on. And Willem was so brave that having many results, and so he was really promising that he will save the situation. Thank you, Willem, for this. And now maybe some information concerning Willem. Maybe it's visible now. Okay, so you see that he's Doctor of Sciences, but not only simple Doctor of Sciences, he is double Doctor of Sciences. He obtained in 1995 Doctor of Sciences degree from Polish Academy of Sciences, and later in 2001 from Masaryk University in Brno. Okay, maybe if we can see some other things. It's very difficult to judge what is more important, whether his contribution in the field of mathematics, logic, and so on, or his organizational efforts and results. So here we see very important date, 1996, he established the Institute for Research and Applications of Fuzzy Models. And it's interesting, as you see, that this is the only one research institute in University Ostrava which still exists. There was a call in Czechia for supporting such new ideas with new institutes, but only few of them survived till now. And of course, also due to Willem and all his team, Irafman is among them. He was the first director, and he was director, you see, for 24 years. Now I hope, Willem, you have more time for mathematics and so not being more head of department or head of the director of this institute. Of course, this has to do also with organization of several events. And similarly, as his institute is co-organizer of fsta, they have either organized as the main organizer or co-organizer of several other meetings, including 2 FSLATs, for example. Maybe this Red Biechine 1990. Maybe you know that in that time still Czechoslovakia was existing. And in fact, we started with fuzzy conferences once in Czechia, once in Slovakia. When it was in Slovakia, mostly it was here not in this building always, but in this area of Janska Voli. This was also mentioned when the concert was, that the tradition of concert of participants started there, and it is alive till now, fortunately. This I am very glad. So Biechine was such first really international event where very important persons from France, Belgium, and so on were present. Maybe what is interesting, what was not mentioned, that in that year, it was later, 1 year, 1991, IFSA was organized by Professor Rubens in Belgium. In that time in Czechoslovakia, in some sense, there were no grants. When Professor Rubens had known this and he had seen the concert of our colleagues, he invited few of them, not only Willem, this was also Professor Riechan, who was mentioned here, or Jarda Ramik. So in some sense, their conference fee and so on was this music performance. So they have brought this idea of concert of participants also to this broader audience. Maybe if we can continue. Okay, so this is, I think, from Biechine. This was this first international event. Biechine is a nice castle, which was in that time in the possession of Czechoslovak Academy of Sciences, but later it came back to original owners, Schwarzenberg's, and I think it's still now in their hands. Yeah. But you have seen that, of course, we were younger in that time. And in some sense, Willem was in the position of scientific head of this conference, and I was responsible for lodging, meals, and so on and so on. Of course, but this was very nice event because in some sense, when you are responsible for lodging, meals, and so you are in direct touch with people. So many of my friendships and collaborations started there, and I believe that also the same happened with Willem. Okay. Yeah, so maybe if you will check Willem's record, it doesn't matter in which database, you will find quite long list. And among the topics, fuzzy sense theory, formal fuzzy logic, maybe what is important, Willem has really enriched and enlarged Pavelka's fuzzy logic. I only recall that for people not knowing Pavelka, take it as a logic based on Lukasiewicz-Tino. Very rough description.
Well,
okay. Linguistic fuzzy logic control, UQ algebras and logics, generalized quantifiers, which in some sense will be also the topic today. Time series analysis with the help of fuzzy modeling methods. This is one of the last topics where Willem started to be involved. Okay, if we can switch decks. Okay. Maybe only I can mention IFSA Fellow Award and this Rector's Award. I think it's related to Ostrava.
It was given by rector of our university, both to Irina and me.
Okay, super. Because, for example, Willem is author or co-author, sometimes also with Irina, of several books. And some of them were really very influential. His Web of Science H-index is exceeding 30, and he was main bearer of several projects. Total budget more than 6 million euros. So I can be only jealous. Okay. And in Biechine, what was interesting, we have invited as a person who should give arguments against fuzzy, Professor Petr Hayek. He came there as probabilist and left as a person starting to support fuzzy. And he has understood that the problem with fuzzy is not that it's not good theory or there are some problems. The problem is if there are presented weak papers, weak results. So this is important to give good sound mathematics here. And I think he succeeded nicely. Maybe you know that basic logics and so on, these are due to Petr Hayek, but the origin, he started to understand these things and worked exactly in Biechine, 1990, which was mentioned. So these are words of Petr Hayek, and this red line is related to Willem. Willem can be considered as a father of fuzzy logic. I will tell not only in Czech Republic, but in Czechoslovakia. Okay. So, Willem, I think it's time to present also the topic which you will present us. So, theory of intermediate quantifiers in fuzzy natural logic. Willem, please, it's your turn.
Thank you. Thank you for a very nice introduction. I only would like to add one story to our trip with Beloriechan and Jarda Ramik to Brussels, where IFSA 91 took place, because we came there and we gave concert in the beginning of in opening session. And later we were told by some people, oh, you are also speaking here. I was plenary speaker in this congress, we thought that you are professional musicians, which was really a big praise for us. And also, when after the session, we met Mrs. Rubens, wife of Peter Rubens, who was the main organizer. And she spoke in French. We couldn't speak in French, but she repeated permanently the word formidable, formidable, and we didn't know what does it mean. And then I looked at the dictionary and I learned that formidable means either fantastic, wonderful, or terrible, horrible.
When you want to drink, be double.
Yes, perhaps, yes. Okay. I will start my talk, as you can see, by comment that I expected that most of you will leave today and only a few of you will remain here. But I can see that at least many of you are here. I think you somehow understand what I'm speaking about. And this is practical example of the use of intermediate quantifiers and in general quantifiers in language. Oh. Let me switch it. Yes, now. So I will first say only a few words about fuzzy natural logic. In 1997, the term natural logic and the concept of natural logic has been suggested by famous linguist, American linguist George Lakoff. And the idea was simply to establish a system of logic which is based on the use of natural language, because people, when they are thinking, they are using always natural language. You can test yourself anytime, and I think that you will believe that this is indeed true. I tried to follow this idea, but because Lakoff is logician, linguist and logician too, but I would say philosophical logician, his theory was not based on mathematical results. And I tried to establish something which I call now fuzzy natural logic. This definition is a modification of original Lakoff's definition that it is now considered as a system of mathematical fuzzy logic, which enables us to model terms and rules that come with natural natural language. This is from Lakoff, and allowing us to reason and argue using tools developed in it. And it requires mathematical model of linguistic semantics. And this can be done using type theory. Namely, in our case, because we extend it to fuzzy, and my example with many of you and so on is a typical example that this expressions is vague, it is not precise. So it should be fuzzy type theory. The arguments why, say, first order logic is not sufficient for modeling linguistic semantics have been given for many, many years by linguists and logicians. So I think they are quite convincing. I will not repeat them. And so far, fuzzy natural logic consists of three essential constituents. It is the theory of so-called evolutive linguistic expressions. You can see example. The theory of fuzzy and intermediate quantifiers and generalized Aristotle syllogisms. This is the topic of today. And also the theory of fuzzy linguistic if-then rules and logical inference. The idea is that everybody knows fuzzy if-then rules, but they are generally interpreted as fuzzy relations. But I think it is, for me, it was not sufficiently satisfactory, and I tried to develop or modify this theory that these fuzzy if-then rules are taken as conditional clauses of natural language, and they are interpreted, their semantics is interpreted in this sense, and therefore the reasoning is slightly different from what you know, for example, by compositional rule of inference of Lotfi-Zadeh. It is not criticism of Lotfi-Zadeh, simply this relational model of fuzzy if-then rules serves for different purposes. But for modeling reasoning of people, this is not sufficient. Generalized quantifiers, there are several names. In fact, this theory of generalized quantifiers started already in 50s of the previous century. Here are some names, and most distinguished among them is Mostovsky, who wrote, I would think, the first paper on generalized quantifiers, and also Paul Lindström. Dag Westerståhl, for example, famous Swedish logician, contributed very significantly to this theory. But his theory, the theories of all these people do not include vagueness. They are not fuzzy. They are classical. They argue, and here are many examples, that many sentences of natural language can be logically analyzed using generalized quantifiers. I will not read everything, but you can see all students cheat, some students cheat, no more than most male and all female, or more students than teachers work hard, not as many boys as girls pass the exam, and so on and so on. Thousands and thousands of sentences of this kind. Generally, quantifiers in logic, I think the most established and so far used definition is due to Paul Lindström. And so the definition starts with some formula of some formal logical language and a model. And we define a satisfaction set of this formula, which is a set of all elements for which this formula is equal in a given model to 1. And so quantifiers are determined by subsets of this of some arbitrary set. And generalized quantifier, you can see of type K1 to Kn, you can see mentioning when you see some literature on quantifiers that the given quantifier usually is of type 1, 1. So this relates to this definition, and you can see that this quantifier is a functional together with certain symbol of the formal language, which to each set assigns a relation over relations. So it is really quite complicated mathematical structure, and so that it holds that the truth degree in a model of such formula with respect to say n other formulas is equal to 1 if the n-tuple of such satisfaction sets belongs to this relation of fuzzy relations. So this is classical definition. If we come to not yet fuzzy. Here are some examples. So typical example is for all. It is equal to 1 if satisfaction set belongs to this set, which contains only just one set, and this is the whole universe M. There are quantifiers of type 1. For example, some boys play hockey. It means that the satisfaction set of all boys should be subset of satisfaction set of those who play hockey. Here is definition. I put here question marks because this definition says that most means simply prevailing half. So if something is more than half, it is most. I argue that it is not correct explanation and interpretation of the quantifier most. It is used in all elections and or voting in committees and so on, but it is not a satisfactory definition of quantifier most. And of course, in these definitions, no vagueness is involved. So if we come from or generalize the given theory to fuzzy, we obtain the following. This claim you can believe or not. I believe that it is true. And again, we can define generalized fuzzy quantifier of the same type is a functional together with a symbol, which to each set assigns a fuzzy relation over fuzzy relations. So saying blindly, we can say that I added only the word fuzzy to the classical Lindström definition, but it is more than this because it requires a well-established formal logical system. So this definition again, here only truth one is replaced by some arbitrary truth with respect to algebra of truth values. Again, example, the universal quantifier. So this satisfaction set, not satisfaction, this set, this functional is a set of all fuzzy sets of the set M, such that membership degree of each of these fuzzy set is infimum of all membership degrees of elements M belonging to this fuzzy set. So what we obtain, in fact, is the usual definition of universal quantified formula in mathematical fuzzy logic. Everybody knows that this quantified formula is computed using the infimum operation. Zadeh came with the idea of fuzzy quantifier, and many of you are using his results, transforming what he established into the definition of Lindström looks like this. So we say that Zadeh's fuzzy quantifier is this set of fuzzy or fuzzy set of fuzzy relations with some symbol, of course. So these are fuzzy relations. This is a quantifier of type 1,1 with respect to the Lindström definition. So that the truth value of this quantified formula is equal to some truth value ABA, if and only if these two satisfactions fuzzy sets are true in this fuzzy set in this degree ABA, and this ABA is this what you know from the paper of Lotfi Zadeh. So this is in fact his definition, and his definition contains FC is a fuzzy cardinality, what he suggested, and he added also a sort of evaluation. Some people say that this is just quantifier, but it's not sufficient. The quantifier is not only this evaluation, but the whole formula realizes Zadeh's quantifier. Now about intermediate quantifiers. In general, semantics of quantifiers in natural language is determined as follows, but in natural language, these quantifiers are words or expressions that precede and modify nouns, and they specify quantity of specimens in the domain of discourse having a certain property. So I am just speaking here about this special case, which is most widely used and most useful. So Q, B are A, where B and A are properties, and Q is a quantifier. And then here are examples. Most women in the party have long hair. Several dry trees are very high. So these are quantifiers of type 1. Sorry, in the beginning you saw it on my first slide, but I forgot to emphasize that the results which I am going to present have been obtained in cooperation with my colleague Petra Murinova, so she shouldn't be forgotten in this talk. What we are relying on is the wonderful book of logician Peterson, Intermediate Quantifiers in Logic, Linguistics, and Aristotle Semantics. He did really very good work, but in this book, the theory, the syllogisms, the quantifiers are analyzed again without using formal means, and therefore we, in some sense, are using the results of Peterson, but we try to formalize and try to demonstrate or mathematically prove that his conclusions are correct, that they are true. What is important is the notion of size of a fuzzy set. Lotfi Zadeh considered cardinality of a fuzzy set, but the quantifiers are used also in expressions such as most or a little of the volume of the box, of a bottle, of a pool, or whatever. Simply, what we need is infinity. And therefore, cardinality cannot work for that, because coming to infinite cardinalities, we would get immediately lost. And therefore, in the definition of quantifiers, we must play with measure. It is a natural way how a size of a set and fuzzy set can be characterized. And the main idea how to model the meaning of intermediate quantifiers is the following. That these intermediate quantifiers, by the way, the word intermediate, it comes from the idea that the semantics of all quantifiers which I am speaking about lays between the classical two limits, universal quantifier for all and existential quantifier. Everybody knows that, but now we are going to determine quantifiers whose semantics is somewhere in between. So the idea is that these intermediate quantifiers are in some sense these classical quantifiers, but what is changing is the universe of quantification. So these quantifiers are taken over a smaller class of elements. And the problem is that, for example, in predicate logic, we don't have means how to introduce it. Therefore, higher order logic is necessary. And this class of elements is characterized by measure, and it is evaluated by appropriate evaluative linguistic expressions. And hence, what we obtain is a definition and working definition of intermediate quantifier, which is naturally linguistic from this point of view and fuzzy, again, because semantics of these evaluative expressions is fuzzy. So we developed a formal theory of intermediate quantifiers as a special theory within a so-called Lukashevich fuzzy type theory. Fuzzy type theory, well, I say a few words about it. So this is a statement that higher order logic is a necessary tool for modeling of linguistic semantics. And in fact, higher order logic, which is usually called type theory, hence this fuzzy type theory, has been established already by Bertrand Russell in the beginning of 20th century. So the theory is very old, but it has been put to good mathematical background by Alonzo Church and elaborated by other people. Very important results are due to Leon Henkin, who proved, because it is a difficult question how to define semantics of this type theory, and so-called standard semantics cannot assure validity of completeness theorem for this classical type theory. But Leon Henkin showed that if we can relax the definition of standard model into the so-called generalized model, then completeness theorem does hold. And this is a really important result. And so fuzzy type theory has been established as a generalization of classical type theory. In general, I can say that syntax of fuzzy type theory is extended lambda calculus, but it has more logical axioms because we must somehow describe behavior of the algebra of truth values. And of course, it has many valued semantics. Only very few words concerning syntax. All formulas have certain type. And types are composed from basic types, type omicron, which is a type of truth values, and type epsilon, which is a type of objects. And then we form composed types, and each formula has a type. So, for example, A alpha and beta for different types, alpha and beta, are different formulas. And notice this is a very important kind of formula typical for type theory. And it is called either lambda formula, or you can meet very often in the literature lambda term. And you should look at it as simply as a function. It is a sort of materialization of a function. We take all arguments x from some set alpha and substitute them into interpretation of this formula C beta, and what we obtain is just the function. So in general, we can say that semantics of type theory and also of fuzzy type theory is the semantics of functions, nothing else, in fact. Formulas of type Omicron, of type truth value, are proposition. These are most interesting. And important notion is the notion of a fuzzy equality. It is simply reflexive symmetric and with respect to a T-norm, transitive fuzzy relation. For our model of intermediate quantifiers, we bound ourselves to standard Lukashevich MV algebra. This is, I think everybody knows these formulas. Notice this delta puts everything, all truth values which are smaller than 1 to 0, and keeps only truth value 1. So it is a sort of, say, discovering Boolean structure in a fuzzy structure. Then semantics of fuzzy type theory is a system of sets with a fuzzy equality. So for each type, this is a set and the corresponding fuzzy equality defined on this set, and the algebra of truth values, which in our case it is Lukashevich MV algebra, but it can be in fact any algebra. Some years ago, I developed a special algebra for fuzzy type theory. I call it EQ algebra, EQ for equality, simply taking fuzzy equality as the basic connective in this algebra. Because what is very nice, and this was done by Leon Henkin already in type theory, the type theory is established and all connectives are formulated on the basis of in his case equality, and this is really very nice, and I like this, and I followed this idea using fuzzy equality, but it required also special algebra of truth values. MV algebra is a special case of EQ algebra. Here is example. So if we have formula A of Omicron, its interpretation in a model M is a truth value. Essentially, in our case, it is some truth value from interval 0, 1. Interpretation of formula A epsilon is some element from the set of all elements. Interpretation of such a formula is simply a function from a set M alpha to set M beta. And this is what I said. It is interpretation of lambda formula, which is again the same function. If we take a theory in fuzzy type theory, so it is a set of formulas determined by special axioms, and the following theorem can be proved. A theory of fuzzy type theory is consistent if and only if it has a general model. This is what I said. So it is a Henkin concept, a general model. And for every theory of fuzzy type theory and every formula of type truth value, such a formula is provable if and only if it is true in all models. So this is completeness theorem, which enables us to derive many interesting results. So now I will come to quantifiers. First of all, we need a measure. It is realized by means of a certain function. It is a binary function, and the reason is that we somehow work with the universe of quantification and fuzzy subsets of this universe of quantification. For finite sets, this formula is used. This is quite common, and in principle, it is the same what was used already by Lotfi Zadeh. Now, a few words about evaluative linguistic expressions. Many of you have heard already this, so I will very briefly say that these are special expressions of natural language using which people evaluate phenomena and processes around. So we couldn't say interesting things without evaluative expressions. We can say there is a woman. Well, but if I say there is a beautiful woman, it is very much different information, especially, of course, for men. Or we can say there is a pond. Well, it is a pond, but if I say it's a very deep pond, again, it is information which is valuable. So here are examples of these evaluative expressions. And in our theory, we deal with simple evaluative expressions which have very simple structure. It is a hedge, linguistic hedge, and what I call TE adjective. TE means trichotomic evaluative. So this is adjective which is basically something like small, medium, and big as a canonical trichotomy. Here is example, very small, of such a simple evaluative expression. Because we are dealing with semantics of natural language, I always try to learn also from people outside fuzzy community and from linguists and from logicians. And therefore, what we need, the logicians introduced the concept of possible world. For evaluative expressions, I replace this possible world by the term context, which, as you can see, is a triple of numbers. You will see what does it really mean. But what is necessary is to say that semantics of all expressions of natural language or of all words with full meanings of concepts is done by the notion of intension. So we can say that these words with full meaning are simply names of intentions. And intention is a function from the set of all possible worlds, or in our case, from the set of all contexts, into a set of all fuzzy set over some universe U. And given one context, one possible world, what we obtain is an extension. So this context here is for example, 0, 4, and 10. 0 and 10 are lower and upper bounds, and 4 is a typical medium value in between these values. The idea here, which is that I argue that in human mind we always deal with bounded scales. And these scales, moreover, are linearly ordered. This is quite natural for human mind. And even if we say the set of all real numbers from -infinity to +infinity, in our mind, I argue, we cannot imagine what does it mean infinity. This is some left bound -infinity and a right bound +infinity. And again, in our mind, we deal with this as a bounds of a scale. Then extension of all expressions which are small lay to the left from this typical medium value. Extensions of all expressions big are lay to the right of this medium, and medium values lay around this typical medium value. In fuzzy set theory, we obtain this curves which represents in fact extensions of fuzzy sets with respect to the given context. What we need also in quantifier theory on our model of intermediate quantifiers is a cut of a fuzzy set. It is very simple idea because originally we worked with a fuzzy subset of this given universe, but we found that it is counterintuitive. If you take, for example, this fuzzy set B, you can see that, for example, the element B belongs to this fuzzy set in a degree 1. But any fuzzy subset of this fuzzy set B can contain the element B with some arbitrary degree, 0.6 and so on. But what for? Why? Why it should be smaller than the given membership degree in the given universe of quantification? And therefore, the idea is to consider arbitrary set which picks out singletons from the given universe of quantification. This is very simple concept, but it turned out to be quite powerful and very well suited to formalization. And now about what, so first of all, intermediate quantifiers are special formulas of fuzzy type theory, and moreover, special formulas in a special theory of fuzzy type theory. We deal with some evaluative linguistic expression. I will often use this meta variable EV. So you should by EV understand some expression, or better say formula for expression like big, very big, and so on. And we also need a measure using which we measure size of fuzzy sets. And then the formula representing or construing expression quantifier B or A is constructed as follows. We take certain part of the universe of quantification B and we consider all x which have the given property A. Then we evaluate size of this part by the given evaluative linguistic expression, and we take the part, here is greatest, but the part doesn't need to be greatest. What it assures is the greatest truth value. So the greatest truth value of this formula is assured by using this existential quantifier, which in fuzzy logic is modeled by the operation of supremum. What is also important, and it can be formally very well justified, is the notion of presupposition. Sometimes in logic you can see also the concept like existential import. It is simply assuring that this universe of quantification in this formula should be non-empty. Only in classical logic this means that there is some element belonging to the universe of quantification. Here it means only supremum. So this universe is non-empty, but there is not necessarily one concrete element having truth value 1. There are definitions. First of all, in fact, definitions say that classical quantifiers, universal and existential, are included in our theory. There are special case of intermediate quantifiers, the limit cases, and this definition very well fits. It's a proof that this really does hold. And then we can introduce other non-classical quantifiers using various kinds of evaluative expressions using which we evaluate size of this part B cut by fuzzy set Z. So here are the other definitions. Most is defined using evaluative expression very big. Many is defined by expression not small. Then also a few and several, they are defined using evaluative expression positive significant, positively significant small and positively very small. The reason why is there a positively, it means that we have to exclude the possibility of zero. This relates to quite understandable if I say, for example, a few people are laying on the table. It cannot mean that there is nobody laying on the table. At least one, of course, must lay on the table. Otherwise, this sentence would have no sense. If it had sense, then I can say that, for example, there are big pigs running in this, a few big pigs are running in this room. Nobody see any pig, but simply such a sentence has no sense, and therefore bounding to positively small is necessary. semantics, our formula might seem to be complicated, but I argue that it is quite easy to compute. Here is computation formula where universal and existential quantifiers are replaced by the operations of infimum and supremum. Here is the example for most, so I think it is quite understandable. And here is example, for example, the sentence, most people in the party are well dressed. So most is interpreted or modeled by this quantifier Q for very big. And the sentence is construed by such a formula. If we consider a universe with 15 elements and we consider a set of 10 people in the party, then and we consider a fuzzy set of dressed people, then after computation using the formula on my previous slide, we find that the truth degree of such proposition is 0.59. Of course, there can be true in various degrees other propositions with other quantifiers. Then for example, for modeling in computer, we would use that quantifier which provides the highest truth value. Also interesting is the notion of spectrum of a quantifier. It is an answer to the question, what are examples, what are fuzzy sets which represent the given quantifier? In other words, how many is most in a given context? Context is always present and must be considered. So the spectrum is a set of these cups of fuzzy set of the universe of quantifier by fuzzy set Z. Here is the formula how to compute. And for example, with respect to example on my previous slide, spectrum of most well-dressed people in the party, which has 10 people, we learn that it means either 8 or 9 people. So this is most. So also quite useful notion which can be used in applications. There are relations among quantifiers. These relations are simply such implications. So for example, if we know that all B's are A, then we know that almost all B are A. Such implication is provable and it is quite natural. Here are other implications with these letters P, T, and so for example, P means almost all, T means most, all, K means many, and so on. Here is example with quantifier a few. So if we know that many B's are A, then we know that a few B are A, and so on. There are such implications provable. And now I will come to notion of syllogism. So syllogism is a logical argument consisting of 3 formulas. And a syllogism is valid if this implication is provable, which by completeness theorem means that this product of truth values of these propositions is smaller than or equal to the truth value of the conclusion. The syllogisms are classically gathered into 4 figures. This is classical and has been introduced already 2000 years ago, probably by Aristotle. So the first is called major premise, the second is called minor premise, and this is conclusion. There are usually playing with properties of 2 kinds, subject, predicate, and middle formulas, and intermediate quantifiers. So I will give only examples of such syllogisms of figure 1 and figure 2. So of figure 1 you can read, I will not read it. For figure 2, no lazy people pass exam, most students pass exam, some students are not lazy people. For figure 3 and figure 4 also. So there are many. In fact, Peterson in his book demonstrated using informal ways that 105 of such syllogisms with these quantifiers almost, and many are valid. And we proved it in our theory that indeed this is true. And also all syllogisms, because there are altogether 4,000, over 4,000 possibilities, but all syllogisms which are not valid really are also not valid in our theory. So we have many arguments that our theory really works well. Algebraic form of a valid syllogism is here. Again, simply quantifiers are replaced by suprema and infima. So nothing really very complicated. What is interesting, we tried to analyze all syllogisms, and we found that from algebraic point of view, only these three inequalities lay in the background of all logical syllogisms with intermediate quantifiers. It is quite surprising result, and really this can be proved that all these syllogisms are consequence of these inequalities. For the respective figures, we obtain these inequalities, but all these inequalities are provable from the previous three inequalities which I had on my slide. So really, in fact, it is not that complicated. Syllogism of figure 3. This figure 3 is a relation that we consider the middle formula, the middle property, and we argue that if some elements from this middle property have one property and the second property, that the second property can be elements having second property can be inferred that also the first property. Perhaps it's better to say on this example, several old people write interesting novels. All old people have gray, and so this we conclude that several people with gray hair write interesting novels. Formally, it looks like this syllogism, but on the other hand, there are also non-trivial syllogisms which are not true, not valid, because, for example, these syllogisms, a few M are P, and almost all M are S, from which we think we could conclude that some S are P. This is not true and therefore not valid. The reason is in this figure here. This means a few M, this is M, have property P. Almost all S have, almost all M have the property S, but they have no empty intersections, and therefore such a syllogism cannot be valid. Finally, I will say a few words about general square of opposition. It is a scheme which enables us to derive new propositions from the known ones and to estimate their truth value. Again, this square of opposition has been studied for hundreds and hundreds of years. In classical definition, we say that a formula P2 is subaltern of formula P1, which is called superaltern. If in any model, it must be true if the superaltern is true. In fuzzy logic, this reduces to probability of such an implication. Contraries. Formulas are contraries if in any model they cannot be both true, but they can be both false. In fuzzy logic, it means probability that strong conjunction of these two formulas is equivalent with falsity. Formulas are subcontraries if in any model they can be both false, but they cannot be both true. In fuzzy logic, this relates to the probability of this. This is, in fact, Lukasiewicz, in our case, Lukasiewicz disjunction. It is A plus B, but cut by unity. So, for example, 0.6 plus 0.7 is 1, because 1.3 is cut by 1. I said it by, you can see it in this formula. Okay. And formulas are contradictory if in any model can be neither true and both neither false. It means that these two formulas must be provable. And here is straight square of opposition, which was suggested by Peterson in his book. And you can see this means that these formulas are superalterns of these formulas, which are subalterns. Here, this means contrary relation. This means subcontrary relation, and this means contradictory relation. What is interesting, notice here that we have here both contrary relation and subcontrary relation. So neither of these is provable. It is none of them is true. But what is provable that many B's are A and many B's are not A. We can find a model in which these two quantifiers are true, and we can find a model in which, in which these quantifiers are contraries, and a model in which these two quantifiers are subcontraries. On the basis of that, a lot of interesting things can be derived. We can also, if we know, for example, these truth values, then we know, knowing the given relation of contrary or subcontrary, we know what should be formula of the other quantifier. I think it is a very simple thing. And therefore, I came to conclusion. What we learned the concept of fuzzy natural logic. We learned the concept of fuzzy quantifier and intermediate quantifier, which is special case of fuzzy quantifiers. We learned a formal higher order theory of intermediate quantifiers. We learned the theory of intermediate syllogisms, and we also learned what is general squared of opposition with intermediate quantifiers. Concerning further work, we should introduce some other new quantifiers. In fact, this we have done a year ago by adding the quantifiers few and several, which was not the case, for example, in Peterson's book. On the basis of that, we should study new syllogisms and extend the square of opposition. We should study also a cube of opposition. This is already being done. You can find papers on cube of opposition with intermediate quantifiers. There is one thing which I didn't mention here today, and these are so-called Peterson's rules for checking validity of intermediate syllogisms. It is very interesting because he suggested originally 6 rules, which can be reduced to 4 rules, which are sufficient. And using these rules, and he formulated informally, you can really in his case, demonstrate that a given syllogism is valid or invalid. We tried to formalize these rules, and we succeeded to do it. And really, to my surprise, such rules really work. So sometimes checking whether the given syllogism is valid is a lot of work with playing with syntax of fuzzy type theory, which can be quite hard to do. And using these rules, it is quite simple. And it is really interesting that these rules do hold and do work. And finally, we are going to develop a special software on which we would demonstrate our fuzzy quantifiers, and which perhaps could be also used in the future in some applications. So that's all. Thank you very much for your attention.
Thank you a lot, Virilem. We have time for questions, comments. Okay, Irina, please.
Yes. I have technical question. How in practice you select cuts all possible,
all possible
subsets,
yes, all possible sets, because if there is no element equal to some of truth value of some element of the given fuzzy set B, then the result is empty set. That's okay.
Yeah, I understand. Yeah. So, but this means that the complexity of proving, is exponential. Yeah. If you shall really.
If we should do it automatically, probably yes. But in practice, so far we are dealing with finite sets, and so.
And these Peterson rules. So, do they somehow help to reduce?
No.
No.
Well, improving these Peterson's rules are for proving validity of syllogisms. But now here you are speaking about.
He didn't work with cuts.
He didn't work with cuts. This is our invention in our formal theory. The reason is formal, because I can easily add quantifier for there exists that such that. And this is quite good, because then I can do all inferences using this formalized system.
Thank you, Radek. If you can come.
Yes.
I do understand the reasons why you use, for example, product. You could get completely different reasoning. Yes. Another thing, you work not only in a Lukasiewicz logic, but also you in extension with this delta operator. So from my point of view, just to remark, this means that if you get this operator, you will enlarge expressive power of the logic. So from my point of view, this logic is functionally complete. So any function can be expressed by these basic logical operations. So maybe this is also a reason you are using this delta. Usually Bas delta operator is used, but sometimes it's called strict negation.
Yeah, this is Bas delta, and it was into mathematical logic, mathematical fuzzy logic. It was introduced by Peter Hayek in his book. And my first attempts to formalize type theory as fuzzy type theory were without it, but it turned out it is impossible, and I had to introduce it. So delta is indispensable; it must be there. The main reason for Lukasiewicz algebra is, first of all, we need contraposition and double negation, because this is present in semantics of natural language. Without this, many things cannot be said, but they are said. So this really we need. And therefore, for example, product logic doesn't have it. So it is not, because negation in product logic is nasty. Yes.
Thank you. Some other questions or comments? Sometimes you have mentioned also the sizes or how to evaluate the measure of a set using, say, generalization of counting measure. Have you ever used something else, some of works of Vigralak or so?
Frankly speaking, not. It is there. It is in the formalism considered, but it should work in some models. I was thinking about developing model, for example, for infinite sets, but it is a good task, for example, for PhD student.
Okay. Yeah. So last time I'm asking whether some other questions, comments. If not, thank you once more to be. And I pass the word to Martin.
So, just let me wait for the visual support which I need. And the sound support. Yeah, so before I start with closing ceremony, I would like to once again to present a very short teaser to the Youth Flood 2025. Because I was in Riga, I was in Latvia, I will never forget it. The hospitality is excellent. And sometimes it's good not to just view it from the point of view of the organizers, but how the others might view it. So I will present how I view Riga and based on what I would like to invite you there. Please can make it active. Yeah. What can you expect in Riga? It's a shining city, as you can see. It's still not working. You can see a beautiful campus, really, with nice buildings, with beautiful facilities inside. You can expect romantic streets in a beautiful city, which you can really enjoy. Nice architecture, definitely very interesting. And you're clicking, or it's me? Okay, if I switch it on, it works much better, right? I have to learn things also time to time. You can see historical center with lots of historical sites. So sorry, Michal, I didn't mean like that, but you're definitely interesting part of Riga when you are there, but you are not historical site. I was now talking about buildings behind, but you can find also very nice places to rest, to have a beer and so on. I definitely suggest. You can find excellent catering. And you can find especially people who are really, really very good in hosting. Their hospitality is excellent. And friends in Latvia, definitely they are encouraged enough and are brave enough to always order a big portion and to share it. Now they have actually taken a big portion of organization duties, and I think we should share it with them as well. We should help them with organization as well as with being there, because it's really important for the success of the conference. You will enjoy it equally as they enjoyed being in Bratislava, where I took this picture. So from my point of view, there are things to see and reasons why to go to Riga. Am I right, Olga? Thank you. Okay, now let's go to, yeah, mark the calendars, please. The end of July, if I'm correct. End of July 25? 21st July. That's the first. So come there on 19 July to have some time in advance. Okay, now let's go to the closing ceremony of fsta 2024. Yesterday, I said all the Thanksgiving to all people who had to the conference to exist. So once again, Laci, Radko, Willem, Jirka, Andy, all of you somehow contributed, of course, Martin, Oliver. Thank you very much once again. But this closing ceremony slides will be my presentation about something different, about another point of view on this conference. What do you need when you organize a conference? What do you have to work on? What do you have to prepare? First of all, you have to buy a nice nature as an organizer. That's the most expensive thing. You have to pay a lot of money for good weather. You find a good building that gives you all the facilities you need. You prepare a program that may be attractive, that can be interesting. You prepare audio techniques, video techniques. You all do all these things, and you prepare even the area and so on. So when you look at these pictures, which I have just presented, what atmosphere you have? At least I do have a relaxed atmosphere, literally relaxed. But on the other hand, the atmosphere is empty. There are no people. And the conference is nothing without people. And it starts to be interesting and it starts to be attractive and important only when people start to enter, because this changes the thing. And that's why you are the most important people here, not organizers, but you. When people start to come inside, the story changes totally. People start to communicate. Okay, this is not the best. That's not the best way of communicating, but in a moment it gets better. People start to communicate. People start to talk. They have scientific discussion. I know, bola prestávka, hey. People start to discuss scientific things. Deeply discuss scientific things. Heavily. People start to have smile on their faces. They start to enjoy it. They wouldn't enjoy it if they were not there. So people are important. They start to smile more and more. Sometimes they start to even laugh. And a smile on faces is magic. That's the magic of the conference. And that's the magic that is, again, based on you, on attendance. You have to come. You actually can see, you create the program, not us. You were doing actually everything. And if you add even culture, art, can you imagine how much we enjoy the conference as organizers? That much. That much. So again, it's about you, and thanks to you mostly. Because if we didn't base the conference organization on you and on like making it that you enjoy it, it will be a that would be. Luckily, I hope it was not the highway of hell, which was shortly after this song confirmed. So it was about you. Thank you for making it fun to stay at fsta. Please come again in 2026. Please, we will be looking forward to meet you again, for hosting you, and for making our best to make it fun for you to stay at fsta. So the whole team really thanks you for all. Thank you very much. That's it. About you guys. Questions, comments, lunch?
Okay. Yeah. So as you hear me today, it was because yesterday singing, yeah. But I think, okay, it may help. Dear Martin, Radko, boys, Ladislav, maybe some of there, and the old staff. We as participants, we want to thank you very much, because without you, it would be nothing here. Yeah, we are not be here also. So thanks a lot, because it was both relax and also wonderful presentations. I have, I make notes, yeah, and my notes for these conferences are always very thick, yeah. So it's my private measure, better than age index and so on, yeah. So thank you very much for all the efforts. That's all. Thank you.
Thank you very much.